Hello, this presentation will continue talking about perspective. It's part 2 of our lectures on perspective. And in the previous lecture on perspective, we talked about how to project onto a view screen. But as we mentioned there, the formulas we used there lost all information about the depth or the distance from the viewer. So we need to do something with the depth values. So let's recall what went on in the previous presentation. We had a viewer, which I'm representing as a stylized eye, sitting at the origin. So here's the viewer. And it's a top view, so the negative z-axis is pointing downward. The positive x-axis is pointing this way. And here at z equals minus d, we have the view screen. And if I've got a point U at xyz in R3, it was projected onto the view screen to the point V equals x prime, y prime, z prime, where we had the following formulas. X prime was negative d times x over z, y prime was negative d times y over z, comma, and finally z prime equals minus d. We picked z prime equals minus d last time because we're projecting onto the view screen where z equals minus d, but the problem is we lost the depth information. So because of this, we lose all information about the distance of U from the viewer. In particular, the point U could lie anywhere on this line and would project to the same place on the view screen. And we want to have it with a good depth value so that the U's that are closer to the viewer will have a better depth value and overwrite any vertices that are further from the viewer on that same line. So we need to do something different with z prime. So let's try another sort of obvious thing to do, which would be, why not just, instead of using z prime, use z? So the question would be, try instead z prime equals z, keeping the same formulas for x prime and y prime. So for there, we'd have the point, instead of v being defined with x prime, y prime, z prime, v would be defined as x prime, y prime, z. And in fact, we'd be putting the point v right there instead of here. So the x and y coordinates would still give the same position on the screen, but the z coordinate would be up here. Okay, so it's not a bad idea, but it doesn't work very well, and there's several problems with this. So there's a couple problems. Problems with this. So problem number 1 is that if we take this mapping that takes x, y, z, that's the u value, and sends it to x prime, y prime, z, that's negative d times x over z, negative d times y over z, z, this cannot be represented with a 4x4 matrix over homogeneous coordinates. And we saw there were lots of things that can be represented with a 4x4 matrix, including the type of perspective I had in the first lecture, where we lost the depth value, and shadows that we talked about in the previous lecture. But this particular map doesn't work. If we tried to clear the z's out of the denominators by the method we used in the previous lectures, we'd get a z squared here, which is not linear. So that's the first problem. The second problem is that it messes up averaging or interpolation in screen space. And so what I mean by averaging as interpolation means we should be able to take the average of values at pixels and fill in the values for intermediate pixels. So let's do an example of how this messes up. Let's suppose I had the U here. Okay, suppose I have two more U's. I'll put one U, another U up here, and I'll call that U2, which has coordinates x2, y2, z2, and U3, which has coordinates x3, y3, z3, and I project those onto the view screen. Well, U2 just projects here, U3 just projects to itself, right? So sitting here, this is some pixel on the view screen, this is some pixel on the view screen, this is some pixel on the view screen, and of course these, I've drawn the points, maybe not of course, but I've drawn the points so that these things lie on a line. With U2 is approximately, with U is approximately the midpoint of U2 and U3. But on the screen, the midpoint of this pixel and this pixel lies here. And of course, it projects from here, which is nowhere near the real midpoint. So when we're doing averaging in screen space, so averaging or interpolating in screen space, let me go back to black. We're going to expect something like the following. We're going to have one pixel that corresponds to this. I'll call this the pixel. I'll call this V2 and this V3. We've got one pixel here that corresponds to V2, another pixel here that corresponds to V3. Think of these as pixels lying on the screen. So now we're no longer doing a top view. Here's the screen, or the image that we're rendering. And the pixel in the middle, halfway between V2 and V3, would be this pixel here. And the depth value for U2, the depth would be Z2. Let me switch back to blue because we're talking about the blue formulas here. So the depth would be x of V2. The depth value would be Z2 because that was the Z value for U2. And the depth value for V3 would be Z3, but the middle point here, the depth is not the average of Z2 and Z3. It's not equal to Z2 plus Z3 over 2. And so when we're rendering things on the screen, we're always rendering triangles. So we're starting with vertices on a triangle, and then we're filling in the middle part of the triangle with averages. So just like we saw in project number 1, we were rendering triangles with values like color at the 4 vertices, and then the colors are being averaged across. We'd like to do the same thing with the depth. The vertices of the triangles are going to have depths attached, and when we average across the triangles, we want the depths to average too. And that fails here when we set Z prime equal to Z. So we want to do something else that actually fixes both of these problems at once. And that'll go back to another kind of way of computing depth for the depth buffer algorithm. So we're going to do a new kind of depth value. So I've made up a name for this, which I call pseudodist of Z. So this is a function of Z, and its values are used as the depth values that are used for the depth buffer method. And it should satisfy the following properties. So the first property is that we can use pseudodist to tell when one vertex is closer than another vertex. So number one is that, but we'll do it reversely. So, but pseudodist respects distance in the following sense, in that if we have two z-values, z1 and z2, z1 is less than z2 if and only if pseudodist of z1 is greater than pseudodist of z2. So we switched from less than to greater than, but that's not particularly important. When we're doing the depth buffer method, we like to compare two z-values to decide which one is closer to the viewer. In particular, because the viewer is looking in the negative z direction, if z2 is greater than z1, then z2 is from a vertex that's closer to the viewer than z1, at least assuming they're on a common direction of view. And we're only comparing depth for things that are on a common direction of view. And so to compare whether z1 is less than z2, we just check whether pseudodist of z1 is greater than pseudodist of z2. So we can use pseudodist in lieu of the z-values for computing relative distance from the viewer. The other thing is, and this comes back to the near and far clipping plane, is that we're going to have pseudodist of minus n equals minus 1, and pseudodist of minus f equals 1. So this is the near clipping plane, is z equals minus n, and the closest objects that are viewable get a distance value of minus 1. And there's the far clipping plane, where z equals minus f, and the pseudo distance of things at z equals minus f get a value of 1. Okay. So now the other thing, and this seems somewhat arbitrary, but to make it representable by a 4x4 matrix, we let pseudodist of z equal a plus b over z, where a and b are scalar constants. Okay. So if we can take these first two conditions here, we have that a plus b over minus n equals minus 1, and a plus b over minus f equals 1. Okay, and these two things together tell us that a equals f plus n over f minus n, and b equals 2fn over f minus n. If you could just try plugging in these values for a and b, and you'll see these equations hold. In fact, they uniquely determine a and b. And furthermore, since b is greater than 0, remember the f value, the far clipping plane is farther away than the near clipping plane, so f is bigger than n. So therefore, b is greater than 0. So this means that the condition number 1 holds. In other words, pseudodistance satisfies this property here, that z1 is less than z2 if a plus b over z1 is greater than a plus b over z2. So this is what we're going to use for depth values, or what OpenGL uses internally for depth values. Now, to finish this off, we want to say that there's a 4x4 matrix that can represent the mapping in this case. So with the definition of pseudodist that we just gave, our mapping has now become the following. The perspective transformation is mapping a point x, y, z to the point minus d times x over z minus d y over z, a plus b over z. And this we can work out as a 4x4 matrix when we switch to homogeneous coordinates. So let's just do this in the most general way possible. We could do a comma 1 here and do some. Let's try slightly different. X, y, z, w should map to the point. So let's just start off with one homogeneous representation. I want to have something with this value, so that's minus d x over w z over w, substituting in x over w for x and z over w for z, comma, minus d y over w z over w, substituting in y over w and z over w for y and z, comma, a plus b over z over w, comma 1. So here I've just put a comma 1 here, or equivalently, it could go to, and what I'm going to do here is I'm going to cancel out the w's and multiply through by z. So it could go to minus d times x minus d times y, a z plus b w, comma, z. So this 4-tuple is homogeneous representation of the same point as this 4-tuple. So these two represent the same point in R3. Because when I divide through by z, I get exactly these values up here. And now we can give a 4x4 matrix for this. We just read this off. And again, it's easiest to read this off by rows. So I've got minus d, 0, 0, 0, 0, minus d, 0, 0, 0, 0, a, b, 0, 0, 1, 0. So this matrix here is the perspective matrix that we're going to use. In particular, if I take this matrix times x, y, z, w, I get exactly this. I get minus d times x minus d times y, a, z plus b, w, z. And in this way, we get a 4x4 matrix that gives us computation of the perspective transformation when using the pseudodist value for the distance. And this, maybe somewhat amazingly, is how graphics systems typically compute depth. It's not the only way they could have done it, but it's the way they do it because the 4x4 matrix framework is so useful widely that it's also worthwhile making it work here too. So for one last comment here is how the use of pseudodist affects the resolution of distance. So pseudodist and resolution of distance. So what I mean by this is the level at which you can discern differences in distances. So typically we use a 32-bit integer for pseudodist values. Okay, or depth values. And we don't, although we've been talking about them as if they're floating point numbers between -1 and 1, we just uniformly use numbers, 32-bit integers, to represent numbers linearly between -1 and 1. And this is usually enough precision. But it's not always enough precision. You can have problems with this. In decades ago, when people first started using the depth buffer method, they used 16-bit integers. It obviously often was not enough, but 32-bit integers work pretty well. But nonetheless, it's interesting because to look at what's the effect of using pseudodistance instead of actual distance. See, the pseudodistance is a nonlinear function, right? So pseudodist of x, or of z, I should say, is a plus b over z. And so let's draw a graph of this, just to be, draw the graph going in the usual direction. Think of this as the negative z-axis, and this is the value of pseudodist. So here is z equals minus n. This is the near clipping plane. And here's z equals minus f. This is the far clipping plane. And remember, the pseudodist function has value minus 1 at z equals minus n. It's got value plus 1 at z equals f. And it looks like a shifted 1 over z function. It's shifted by, it's actually b over z, and that's shifted by a. And so it looks something like this. Now, how steeply it slopes here versus here depends on the relative values of n and f. If you have too big a difference between n and f, like if n is very close to the viewer so the viewer can see very close things, and f is very far away from the viewer so the viewer can also see very far things, then it does get to be more strenuous. But so usually it's better to keep n and f not too far apart, just to encompass what you really need to see and not more. The other thing to notice, though, and this is what I want to do on this graph, is the slope is steeper here when we're for near objects. The slope is less steep for distance objects. So what this means then is that pseudodist can better discern distances for near objects or can better tell apart differences, better discern or tell apart distances for near objects than it can for far objects. And it's not so good at discerning distances for far objects. But this is a good thing, because if we're rendering a scene, most likely we're interested in details that are close to the viewer, and the further away things, we're less interested in their details. In particular, if we mess up on relative distance of small objects that are far away from the viewer, we may not even be able to see it in the scene. And we really, though, want to get the distances correct on objects that are close to the viewer, because those are more readily seen and more likely to be close to the viewer, hiding further things. So this is a good thing. So this is good. Okay, that's the end of this presentation. Thank you very much.